Good evening, everyone. Welcome to today's webinar where we embark on an exhilarating journey into the world of quantum computing. I am Manya Gupta and I am the Business Development Engineer at Panda Applications. And today we are gathered here not just to talk about the future but to glimpse it firsthand. Let me introduce you to all our speakers for today's webinar on quantum AI for real-world computational data. Mr. Advait Gupta is the CEO and founder at Panda Applications. He is also the founder of the International Simulation Olympiad. Mr. Advait is a MS from Stanford University and holds expertise in computational physics, CFD, and AI, etc. He is also the developer of AM Prava and DC Prakar. Next, we have Mr. Mateen Ahmed. He is currently serving as software engineer at Paanduv Applications. Mr. Mateen is a MTech from Defense Institute of Advanced Technology and possesses a strong skill set in Python programming language, machine learning, and data modeling, etc. Paanduv Applications is based in Bareilly, Uttar Pradesh, India. It is a cutting-edge technology company that specializes in providing comprehensive computational physics, AI, quantum computing, and software development services. In the realm of quantum computing and AI algorithms, fiction becomes the blueprint for tomorrow's realities, bridging imagination with innovation. Therefore, let's deep dive into the world of quantum computing. Hence, without any further ado, I present to you Mr. Advait Gupta.
Um, Thank you, Manya, for the wonderful introduction about quantum computing. So let's get started with fiction, and we'll get to the real stuff as we move along with the presentation. So over the last 1 decade, or probably starting, around 2007, there was an onslaught of a lot of science fiction movies, a lot of superhero movies, focusing a lot on, or basically focusing a lot on the consequences of mingling quantum computing or quantum mechanics with everyday activities. Where we have seen superheroes fighting each other in the quantum realm. We have seen quantum computers with the help of AI predicting the future. We have seen chaos theory being solved by quantum computing and computational mechanics. All in all, this has been a great fiction, a lot of inspiration for how the future of quantum computing would look like. But if we talk about the reality of it, great things, great innovation doesn't just happen overnight. It's been more than 40 years since Richard Feynman and Yuri Manin for the first time proposed the concept of a quantum computer. And thereafter, many more developments happened. The most significant ones, personally, that I feel were the discovery or conceptualization of the Shor's algorithm and the Grover's algorithm, which are still heavily used and will continue to be used by many industries across the globe. In the year 2000, we actually saw the first experimental implementation of Shor's algorithm, and D-Wave, the quantum computing company, built the first 16-qubit quantum computer. Moving to 2010s, we started seeing IBM's 20-qubit quantum computer, and Google ended up building 53-qubit Sycamore processor, or a quantum computer again, which basically was started performing better than some of the classical algorithms. Moving to the very latest stuff, I'm talking about 2020s. IBM has announced a 127-qubit quantum computer, breaking the 100-qubit barrier, and Google is introducing more and more complex quantum computing algorithms. While it's been 40 years, but the research goes on, and there's a lot more to be done before quantum algorithms can be fully deployed in their full-fledged capacity to especially to the fields like material science, pharmaceuticals, uh, weather forecasting, and things like that. Uh, Taking a quick look at India's strategy towards attaining quantum superpower by the end of 2030, the Indian government has declared a 730 million USD grant uh, towards building an indigenous quantum computer by 2030. So that's in the next 6 years. The aim of these quantum computers would primarily be improving their quantum communication within India and other countries. Um, the major application area that the Indian government foresees, in fact, many of the governments foresee the most vibrant use of quantum algorithms in areas like communication, health, finance industry, energy sectors, drug design, space, banking, and security. And Indian quantum mission is fairly aligned with these global goals as well. So where do we come in the picture? What has Paanduv got to do with quantum computing? So inherently, we are a computational physics company wherein we take difficult equations of physics, which and then try to solve them numerically using high performance computers, and then these algorithms can be deployed across multiple industries in improving their process designs, in improving their pipelines, and at the end of the day, improving the accuracy of their processes and reducing money, reducing the costs. So from computational physics, we moved to artificial intelligence, where we started using AI to enhance or improve the accuracy and reduce the turnaround times of the computational physics model. And then we realized that why not we should try quantum artificial intelligence algorithms and see if quantum AI algorithms provide any advantages over classical AI when we are dealing with very realistic industry grade computational data. Okay. And as the title of the webinar goes, we have actually achieved breakthrough accuracy with the quantum AI algorithms when compared to the classical AI algorithms. Yeah. So what is quantum computing? Again, there's an immense amount of literature available over the internet to understand what quantum computing is, but to put it in simple terms, quantum computing takes advantage of the principle of quantum mechanics, and in doing so, it can solve complex problems that classical computers either cannot solve or they will take forever to solve. Classical computers work on bits, 0 and 1, and quantum computers, they work on qubits, taking the alphabets Q, U from the quantum, wherein the qubits are basically a probabilistic model, such that if you look at the classical computers, your switch can either be on or off. Either it's a deterministic system where everything is either happening or not happening. But when you start looking at the quantum systems, it's basically a superposition of all realities, wherein your switch can be turned off and turned on at the same time with certain probabilities. Okay, so this is this principle of superposition, which is not a human artifact, but exists in nature inherently, is what is fueling the power of quantum computers. Okay. Just for the sake of visualization, a typical quantum computer or typical quantum algorithm can be represented with the help of quantum circuits. Just like electronic circuits, you can make your very complex quantum circuits where each qubit, in this case Q01, Q02, Q03, or perhaps the different states of the same qubit, they can go through a lot of gates such as Hadamard gates, and other gate manipulations to basically provide you the final state of that qubit. It could be 0, 1, 2, and then you superimpose all those states to arrive at the final answer. Anyways, I really would urge all the everyone in the audience to go through the quantum mechanics, the quantum computing. It's really really cool stuff to know in these times. While there are different approaches to quantum algorithms, the one that we'll be focusing, or that the one that we have focused the most so far, is the hybrid quantum classical algorithms, and that's what forms the backbone of Quant Prakar as well, and we'll see that as we move forward through the webinar. Okay, so this is what Paanduv has done in terms of connecting computational physics data. We take computational physics data, put it through classical AI algorithms, and then we also put it through quantum AI algorithms and try to see if there is any improvement. There is another aspect to it. We just didn't want to see. We just didn't want to do this exercise to create to see which one is more accurate. We also wanted to genuinely become a part of the global quantum mission and add our contribution to the education of quantum computing. It could be among the students, professionals, professors, faculty, researchers, and even working professionals. So right now there's a bit of a disconnect between learners and the quantum world, and there are a couple of reasons why this disconnect exists. So quantum mechanics is a scary word. It is complex, to be honest, and that basically provides resistance to even the most spirited learners to stay away from this whole quantum ordeal. There is a very limited access to real quantum resources. Fortunately, there's a lot of simulated quantum computers can be generated in your own laptop, but still the access to real quantum resources is limited, simply because there aren't many quantum computers in the world right now. The abstracts of the quantum, the concepts of the quantum computing or the quantum mechanics are quite abstract, and they are not difficult to grasp based on what we observe in our everyday life. And then lastly, there's a lot of lack of educational resources. When I say there is lack of educational resources, I mean, the Google and other IBM and other companies have done a great job providing open source libraries such as Circ, Qiskit, PyQuil, but it's not a very straightforward task to even use these open source libraries at times. So question is, who can use quantum AI? And the answer to that question is pretty straightforward. Pretty much everyone can use quantum AI. It could be for the security purposes, it could be for agriculture, banks, military, defense, pharma, space technology, weather forecasting is my personal favorite, encryption, making sure your credit cards are not easily hacked. So basically everything that you're using AI for right now, at least the quantum AI can be right away used for those applications. Again, when I say they can be right away used, theoretically they can be right away used, but it requires a lot of validation work, a lot of research work before we have the actual numbers to showcase that. Okay. And that's exactly what we are going to do today with a couple of case studies. But we'll start with the one that has the real data from real industry grade data, and we'll show how we have achieved the breakthrough accuracy using that data. So recently we had an opportunity to work with the world's largest social media company on their data farms, and we ran a lot of computational fluid dynamics or computational physics simulations for those guys, wherein we wanted to minimize the heat island effect that is caused when a large number of cooling units are placed next to each other. So these narrow galleries between each dry cooler or the cooling unit, there's a lot of potential of heat accumulation in that area, basically reduces the overall efficiency of cooling in these data centers. Now it's very important that these data centers are cooled in a very regulated manner, because all our personal data at times is saved on these very servers that we were trying to keep below a certain temperature. Okay, so the challenge of cooling, the challenge of arranging these dry coolers was not straightforward. The computational physics, while it gives a lot of accurate results, it can be very time consuming, and you need to run a lot of simulations before you can conclude whether a particular design is appropriate, design of dry coolers, orientation of dry coolers, given the type of city you are building, this data farm, data center, based on the wind velocity, direction of the wind, ambient temperature, the company you are buying the dry cooler from, based on all these 15 to 16 parameters, you have to decide one simple thing: how much will be the heat island effect in these data centers. So we started off with a lot of computational physics simulations, but once we had enough data, we decided to deploy pure neural networks or classical AI on these, so that for the remaining predictions, we don't have to run as many computational physics or computational simulations. We can just quickly, based on the learnings from the previous simulation data, our classical AI model can quickly predict what is going to be the outcome if a different set of parameters were to be chosen. And we basically wrapped this in a piece of software called DC Prakar or data center Prakar. Okay, so that's the history behind this data. So like I said, this data, basically the input is what dry cooler it is, what is the arrangement of dry coolers, are they stacked 3 into 2, are they stacked 2 by 2, are they stacked 6 by 1, what is the ambient temperature, wind velocity. So in total around 15 parameters that decide the final outcome of the amount of heat accumulation or heat island effect, right? So once we were happy enough, once we attained an accuracy of around 84% accuracy of prediction using the classical AI models, we then started thinking, why not throw this data at the quantum AI algorithms and see if anything changes. I mean, basically started off as a curious, as an activity to satisfy our curiosity, but what we got out of the results was quite shocking, to be honest. So we tried different algorithms. We tried the support vector machine, the classical support vector machine, the classical artificial neural network, and then we tried the equivalent quantum support vector machine and the equivalent quantum neural network for the same set of data. And here are the results. If you look at the quantum support vector machine using the classical quantum approach and the quantum classical approach, and I'll talk about it a little bit, versus the classical approach, we are definitely getting better classification accuracy. So CQ approach means your data remains as it is, but you modify the quantum algorithm, okay? And the QC approach means you modify the you modify the data in a way that it can be utilized basically with the quantum algorithms. You basically pre-process the data in a quantum manner, but then you deploy your regular classical support vector machine. And the classical just means CC, which means classical data, we don't change the data, and classical support vector machine. So that's not hybrid at all. Okay. And we tried, again, these are very deep concepts, require a lot of time, different types of feature maps, ZZ feature map and Z feature map, but I'll conclude all this in a simple manner, that the ANN validation accuracy, and then we tried the same set of data for the regression problem, where rather than classifying whether a heat island effect is happening or not, yes or no, We are trying to exactly quantify what is the amount of heat island effect, how much degrees of temperature rise is happening. We did this with artificial neural networks, and then we also did it with quantum neural networks, and the accuracy went up from 84% to 92%, which, to the best of our knowledge, with such a large feature set, is one of the most unique studies in the world, and we are really proud of our team that we have been able to accomplish this. Okay. So that brings us all to the question, when and how can I start using quantum AI? And I will let my colleague Mateen Ahmed to talk about this, and yeah, let's see how we can start using quantum AI.
Yes. So, hello everyone who's watching us. Thanks for joining. And first of all, I would like to thank Advait for setting up the context. Now I think we can go forward looking what we have done in this quantum AI domain. So, when and how can I start using quantum AI? That's a very basic question which one can ask. So, the simple thing is, in about 30 minutes, maybe less than that, you will learn how can you use quantum AI with a software that is Quan. So Quan will be available to you. All you have to do is, in this description box, there's a link available. You can just press on that link and you can go fill out the form and you will receive a copy of Quan from our end. So without further ado, I think we should move on to the next part. So yeah, now the product is out there, product is launched by us. So the Quan is the name of the product. What it does is basically, you can use it for the quantum AI purpose. So again, there are various classical algorithms that are out there. So like those, we have quantum AI algorithm as well, right? So you can see over here, SVC, ANN are the classical approaches, whereas the QSVC and QNN are the quantum approach to these algorithms. So you can train your model and you can use it for the prediction purpose. You can hyper tune your parameter and you can build more and more robust model using the software. Quantum circuit visualization is also something which you can do. We will see all this just in few minutes. So yeah, so a dedicated prediction window is also available, so you can use that too. Moving forward, we see this is a graphical user interface for Quan. On the upper left corner, there's a Quan logo which is present over there. This is the logo. Here you can see the flow chart. Now this flow chart is nothing but a representation where are you at the current moment while doing the operation. You will learn frequently in a minute, okay? And below you can see the navigation bar. Navigation bar is nothing but it will tell you which part you are at the moment, okay? Basically, if you want to train your model, you can click on this button over here. And if you want to go to the prediction window, there's a separate button. We'll see that in the demo once again. So I'll tell you what the workflow is. It's start basically an idea. Whatever the project, whatever the data, if you have, you want to analyze the data, you want to grasp good insights from it. Okay. So all you have to do is you have to upload the data in Quan. What it will do is it will process the data. Then you can select the algorithm. If you are using a quantum approach, you have to select the feature map, right? And then after tuning the hyperparameter, you can train your model. So if you are happy with the results after evaluation, so you can go forward and you can use that model. If not, you can go back and you can do again, you can again basically tune your hyperparameters, and then you can do this process until you get your desired result. Okay, so yeah, I think Advait has already covered this, that algorithm that currently we have, the classical and the quantum AI. This is something which I've already mentioned to you, right? So next part is visualization as well. So it provides visualization feature as well, where you can see the quantum circuit and the loss function after your training. Okay. So what I've done is I've taken a case study. Okay. So what the case study is, I'll tell you in a brief about it. So there's a data set of around, I think, more than 1,000 blocks of concrete. So what we have done is we have made a concrete out of all these components using different proportion of these for sure. So we have cement, we have blast furnace slag in the data set. We have fly ash, water, super plasticizer, coats and fine aggregates. All these data sets we have, and again, yeah, the age is also there. So all these parameters we have used to predict the concrete strength. So this is a experimental data that has been done. What we will do now is we will train our model using this case study, and at the end we'll do a prediction for this particular concrete block, which we have made using cement, these configuration of cement, blast furnace, fly ash, water, right? With these quantity, we'll do the prediction of the strength. Okay, I think now it's a time we should go to have a quick demo. So here is the software AM Prabha. You can see, as mentioned earlier, this is the window. This is a home page basically. Here we have a train model button, and then we have a prediction button if we want to do the prediction part. So first, as we don't have any model yet prepared, so we'll go to train and we'll train our model. So you might have observed that this part has become black, so it means that you are on the next stage. This yellow color over here, it's showing us the progress over the time. So we'll give a name to this project. Let's say concrete strength project. Okay, so we are creating, we have to create a file. Okay, just a second. Now we have to save a data. I'm saving this in the same file in dist. Yeah, I've selected a directory where I want to save this project. Now next part is I have to upload the data set. So I have my data set in this part. So here we have a concrete data set, and I will select this data set and I've opened that. Okay. Next step is I want to select algorithm. Which algorithm? I think before I go forward, I should also showcase you what the data set actually look like, right? So this is a concrete data set. So yeah, for all these different quantity of cement, blast furnace, fly ash, as mentioned, I have the experimental strength from experimental result basically. Okay. Now as I have selected that, I've selected the part to data set. Now I will go for algorithm. So what I'm doing is I'm selecting the quantum algorithm, that to quantum neural network. Okay. Now I will save and proceed this. Okay. Now in this step I have to mention which feature map do I need to select, whether ZZ or Z feature map. So I'm going with the ZZ feature map, Next is the hyperparameter page. So on this, basically, this is a page where you can change various things, whether what is the test size that you want to give. So here I've taken 20%. You have to initialize a random state as or whatever you want, right? Entanglement, which we can give here, you want linear, circular, full, right? Epoch, suppose I'm giving 500 epochs, right? And learning rate, number of folds, how many folds you want to give. Okay, suppose I'm giving it 3 folds. Next is optimizer. Adam is best so far, so I'm going with that only. And then the number of neurons in the first layer. All these data, I have to save this. Then only I can go to summary report. Now, what does the summary report showcase is all the material that you have, all the parameter that you have selected. So here it's showing you a short summary to that. So just for a last check, if you think that anything is wrong, you can go back and you can change that again. Okay. Once you're done with this, you can simply press the train button and this is blue. That means training is happening. So at the same time, I want to mention that terminal is also there, right? And terminal, you will see the progress. So we can see that for first fold, it'll go for 500 epochs. So similarly, I've taken 3 folds, right? So we can see that the pace at which it's happening is fast because the data is simple CSV format data. So training is happening quite fast. So after every fold, it's also calculating the test loss also, right? So we have to wait until, so yeah, it's only, we have only selected 3 folds at this time. So after the 500th epoch of this, it will be finished. Training will be done. Yeah. So what we can see here, we can see after the training is completed, it's showing us the average loss, average training accuracy or loss, right? It's showing us the time it took to train this model. It is showing what sort of task you have given, whether it is a regression or the classification task, right? And after that, it has done the evaluation part also. So these are as these are being done, what we can do is we can minimize this part and we can go to the evaluate model. Now in this evaluate model, what we see is the performance, right? We see the loss metrics. What we see is this the epochs versus loss curve. That as we have increased the number of epochs, the loss is also become because the loss is also reduced, right? Along with this, what we are getting is the quantum circuit also, right? We are also getting the quantum circuit. It's mentioning over here whether which feature map you have selected, ZZ or Z, right? So it is mentioned. And then once this is done, that means you have done the training, you've got the, I know that this loss is 45, it's not a good number. But again, if you want to improve this, what you can do is you can go back, you can change the hyperparameter, you can train again unless you get the best result, right? So now we are done with this training part. What we can go towards directly to the prediction, okay? So now I want to mention one thing. Now look, entire thing is black. Only this part is colorful. That means we are at the prediction window. So very first part is we have to select which algorithm again, as it is QNN, and if it is a ZZ feature map, you have to mention entanglement also. So I've selected linear because I have given linear in my original set. Okay, Now the next thing is we have to upload the model, right? So uh, look, first I will showcase you all the thing which we have created. So this is the project that we have created, right? So here our model is being saved. Once our training is done, model is saved. Along with this, we have a summary report as well as the performance data. Whatever the parameters you have given, that is also being saved, and the pre-processed data is also here, is also saved. Okay. Now we can use our model directly from here for the prediction purposes. So what I'm doing is I'm going, just a second. Yeah, this is a Quan prar. I'm going to project, and from here I can select model.pkl, that's a model file. Now input data set. Now I hope you remember that here I said that on these, after training a model, we'll check whether on these parameters I'm getting good strength or not, right? So I will input the data. So data I've saved here only, this X part basically. I can show you that too. So yeah, these are the parameters basically. Cement value is 380, blast furnace 95, fly ash is 0, water 228. These are the same as mentioned in the slide, right? So once I've selected the data also, all you have to do is I have to press on prediction button, and what I see is prediction is done. So to check our prediction, what we have to do is we have to go to our project, and here we can see that this prediction CSV file, and what we see is it's coming as 39.85, right? Now I do have the original data also for this. So in actual, basically for the same parameter, I see for the same parameter the strength was 39, and with a prediction it is coming a little more than 39, which is actually pretty good comparing to the loss that we had. It's actually pretty good. So yeah, you can see how robust the nature is, right? Yeah, so that's all about it, about Quan prar. How you can, this is about end-to-end process, like how you can begin your project and all. Again, there are various algorithms. We have classical SVC, artificial neural network also, which are quite simple. And then we have QSVC also, where again we give user a chance to select which feature map they want, which sort of approach they are looking for, all these things. And then they can again select from here what sort of test size they're looking for, what sort of entanglement they're looking for, right? So I think you can use in various ways, in whatever the data you have, whatever the industry you belong to, you can use that data to make prediction, and you might get some useful result. Yeah, so that's all about the Quan prar. Let me minimize this. Just a second, it's not coming. I think like that's the end for Quan prar. So again, I want to mention, if you find it useful, so there's a link in the description box. You should totally go to that link, and you have to give few information, and then we will be emailing you, email and name, that sort of information that will be required, and then we will be emailing you the product, so you can make use out of it in your daily life. Yeah, so that's all about Quan prar. Now I think I would like to end it with this very small yet very powerful quotation by Paul Dirac. Like, pick a flower on Earth and you move the farthest star. So it speaks about, I think, entanglement. So, which in itself, like, this is such a short line, yet so much powerful. These are the people who keeps us motivated in what we are doing, right? Yeah. Thanks for now. And what I can say is, like, if you want further update from our end, you should totally definitely you should follow us on, you should subscribe us first of all on YouTube, and you should definitely go check out our website. There we have a section for Quant Prakar also, so you can go to that. There also the form is provided. I don't know why this slide is not opening. I'm checking. Here basically I have provided the QR code. No worries, I'll do one thing, I'll talk to my team. We will be sharing you, the link. Just fill out the form and we'll get back to you. So for now, I think that's all from our end. Thanks for joining, first of all. Thanks to all of you from different part of the world. I see you have joined, and yeah, I see the enthusiasm. It is very much appreciated. We are also very much working into it. So in future, if something comes up, we'll definitely get back to you.